Imagine every sentence a human speaks is a tiny universe of meaning, but computers don't understand meaning. They only understand numbers. So the question is, how do we turn human language into something a machine can reason about? Welcome to Embeddings, the secret engine behind RAG, semantic search, chatbots, and your entire AI automation agency. What is an embedding? Think of an embedding as a fingerprint of meaning, not the words, not the spelling, the idea itself. When we embed text, we convert it into a unique mathematical fingerprint, a coordinate in meaning space, a numerical description of a thought. It doesn't store the text, it stores the semantic meaning of the text. Root canal, endodontic therapy, nerve removal in a molar tooth, 3 different sentences, but one meaning, and embeddings capture that. What is a vector? A vector is simply a list of numbers. That's it. An embedding is a vector, usually something long and detailed. For example, Titan Embeddings V2 returns vectors with 1536 numbers. It looks meaningless to us, but to AI systems, it's a precise coordinate, an address inside the universe of ideas. Why do we need vectors? Computers cannot compare text directly. They don't know spelling variations. They don't understand synonyms. They don't know that root canal and nerve removal treatment are the same thing. But once both sentences become vectors, the computer can ask a very simple question. How close are these two meanings? That closeness is calculated using cosine similarity, a math trick that measures the angle between two vectors. Same angle equals same meaning. This is the foundation of search. RAG, recommendation systems, summaries, and clustering. Real dental example, meaning matching. Let's embed 3 questions. Q1, how much does a root canal cost in Sydney? Q2, pricing for endodontic therapy. Q3, what are your opening hours? Now watch the magic. Q1 becomes vector A, Q2 becomes vector B, Q3 becomes vector C. Cosine similarity might say A and B equals 0.92, almost identical meaning. A and C equals 0.04, completely unrelated. This is how your AI receptionist understands intent, even when customers use different words. That's semantic search. That's why embeddings matter. How RAG works. A patient asks, "Do you guys do nerve removal treatment?" Your system quietly performs 6 steps. 1. Convert the question into an embedding. 2. Search your vector database. 3. Find the closest matching chunk. 4. Retrieve that chunk. 5. Send the chunk plus the question to the LLM. 6. The LLM generates an accurate answer when. Even though the patient never said root canal, the system understands the meaning and finds the right content. That's retrieval augmented generation, RAG. Where embeddings live. Embeddings don't live in S3. They live in vector databases, places designed to store meaning and compare it fast. The most common homes are OpenSearch Serverless, Pinecone, Weaviate, Milvus, runs locally. DynamoDB with vector search, Bedrock knowledge bases fully managed. These systems have one job: find the closest meaning vector instantly. Because in AI, speed is accuracy. Remember this exam trick. Text lives in S3, meaning lives in a vector database. Vector databases, the real engine room. In Pinecone or OpenSearch, each chunk looks something like this. Chunk ID text, vector, 0.12 at 0.05. Millions of vectors, all searchable in milliseconds. This is how your dental chatbot finds the right information fast. If you see an exam question asking, where should embeddings be stored? The correct answer is always a vector database or a service that supports vector indexing. Never raw S3, never plain DynamoDB without vector indexes. Never a relational DB unless it has vector support like pgvector. Chunking. Small pieces, big accuracy LLMs cannot read a 200-page PDF at once. So we break the document into chunks. A chunk is a small meaning block, like 200 words with a little overlap. Koala Dental Price List.pdf becomes chunk 1, chunk 2, chunk 3. Each chunk gets its own vector. That allows the system to pull only the pieces that matter to a given question. Chunking controls: speed, accuracy, relevance, hallucination reduction. Chunking is the backbone of RAG. Cosine similarity, the compass of meaning. Cosine similarity measures the angle between two meaning vectors. 1.0 identical meaning, 0.8 very similar, 0.3 weakly related, 0.0 unrelated, minus 1.0 opposite directions. This is why root canal, nerve removal, endodontic treatment, treatment for tooth nerve all point in the same general direction in vector space. Cosine similarity reveals the meaning, even when the words are completely different. Full RAG pipeline story. Here's how your AI receptionist actually works behind the scenes. 1. The patient asks a question. 2. The question is converted into an embedding. 3. The vector database finds the closest chunks. 4. Those chunks are delivered as context. 5. Claude Sonnet or Mistral reads the chunks and the question. 6. The model generates a grounded, factual answer. No guessing, no hallucination, just meaning-aware retrieval plus control generation. This is exactly what AWS expects you to understand for the exam. Final memory story. Embeddings turn language into coordinates. Vectors store those coordinates. Vector databases find meaning fast. Chunking breaks documents into pieces AI can actually handle. Cosine similarity tells you which ideas live near each other. Put together, this is the engine of modern AI and the heart of every RAG system you'll build.